Section 4.3, acid-base reactions. Okay, we're going to begin by talking about the second type of reaction. We already looked at precipitation reactions. Now we're going to look at acid-base reactions. So there are two types of compounds that we're going to discuss. One is called an acid, and the other type is called a base. And one way of thinking about what an acid is it's a substance that produces the hydrogen ion in water. So if you put this substance into water, it produces the hydrogen ion. Now the hydrogen ion is often written as the H plus ion. So I'll write that it's aqueous because it is an ion, so it will dissolve into water. That's called the hydrogen ion. It is also referred to as a proton. Now, why would we call it a proton? The proton is a subatomic particle. It's part of the nucleus, right? But here's what happens. If you think about a hydrogen atom, a hydrogen atom is a nucleus that typically has a proton, and then outside of the nucleus is the electron, right? The electron is in orbit around the proton, right? So that's a hydrogen atom. Well, what is a hydrogen ion? The hydrogen ion is H+, which means essentially you take the electron off of the atom. And so now what are you left with? You're left with just a proton. So the hydrogen ion is actually just the nucleus of a hydrogen atom. It's a proton. Okay, so that's why it's called that. So there are certain substances that produce the hydrogen ion, or the proton, in water, and they are important in all sorts of biological processes. And so I won't go into details in that right now, but if you take a look, you'll see that all kinds of acids or proton donors or protons or hydrogen ions are important in all sorts of biological processes. Okay? There's a second type of compound that you may be less familiar with. And that's called bases. And bases produce hydroxide ions in water. And so the hydroxide ion is OH negative. It's written this way. Okay? Can also be written as HO negative, either way. Okay? Hydroxide ion. So it's also important in biological processes. And what's significant about it is that if you take a hydrogen ion in water and combine it with a hydroxide ion in water, they will very rapidly and energetically, very forcefully, vigorously form a water molecule. Okay? They react with each other pretty significantly. So the hydrogen ion and the hydroxide ion, you should be familiar with those names, be familiar with their chemical symbols or chemical formulas are. Those are what we're going to talk about. Now, if we consider table 4.4 from your textbook, okay, this is on page 140, that has a table of what are called strong acids and strong bases. And you really, it's a good idea to just, I would call it a requirement that you memorize these. Okay, memorize them. So let me go over these two lists. Let's do the strong acids first. Okay. So the strong acids are HCl, hydrogen chloride, HBr, HI, HNO3, H2SO4, HClO4, and HClO3. There are 7 of them, and their names are hydrochloric acid, hydrobromic, hydroiodic, nitric, sulfuric, perchloric, and chloric. Chloric. Chloric is the HClO3. Perchloric is the HClO4. Sulfuric is the H2SO4. Nitric is the HNO3. And you can see that hydrochloric is the HCl. Hydrobromic is the HBr. And hydroiodic is the HI. Okay, so those are called strong acids. These are materials that when you dissolve them in water, they form hydrogen ions, H plus ions, or protons. They react with bases, and that's an important aspect of what acids are. They react with bases. So next, let's take a look at the strong bases. These should also be memorized. If you want to go through these now. So there are 8 strong bases. LiOH, NaOH, KOH, RbOH, CSOH. 5 there, and then there's 2 more. There's 3 more. There's CaOH2, SrOH2, and BaOH2. Okay, 8 of them. And their names are lithium. So you name the metal, and then you name the hydroxide ion. Okay, so lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium, cesium. By the way, all 5 of those are alkali metals. Those are just the alkali metals. And then there's calcium hydroxide, strontium hydroxide, and barium hydroxide. These are 3 of the alkaline earth metals. Okay? So there are 8 strong bases. They are the alkali metal hydroxides, which have 1 hydroxide each, and then 3 of the alkaline earth metal hydroxides, which have 2. Now, the reason that beryllium and magnesium hydroxide are not included, they are alkaline earth metals as well, is that they do not dissolve. Their solubility is very poor in water. So since they cannot dissolve, they cannot form a large quantity of hydroxide. So they're what are called weak bases. Okay? Now let me show you a way to represent the process of dissolving acids and bases into water. So if we take HCl, and it turns out HCl is a pure substance, is a gas, actually, hydrogen chloride. You can buy it in a gas tank, a gas cylinder. If you dissolve it into water, so this is the way we'll represent that process. H2O is being dissolved into water. It essentially behaves like a soluble ionic compound. It forms 2 separate ions that are dissolved in water. So it forms the hydrogen ion and the chloride ion. And since HCl is a strong acid, if we were to put 1 mole of HCl into water, then essentially what it would do is it would dissolve to form 1 mole of hydrogen ions and 1 mole of chloride ions. So there wouldn't actually be much in the way of HCl in the water. Once it gets into the water, it dissolves, it ionizes to form the hydrogen and chloride ions. Now, if you take a look at the strong bases, it's a similar process. For example, sodium hydroxide. Sodium hydroxide as a pure substance is actually a solid. And when you dissolve it into water, you get Na plus sodium ions, but you also get the hydroxide ion. Okay, and again, if you put 1 mole of sodium hydroxide into, let's say, a liter of water, you would get 1 mole of sodium ions and 1 mole of hydroxide ions, meaning 100% of it would dissolve to form sodium and hydroxide. So in the water, you wouldn't actually have sodium hydroxide, just as you wouldn't have hydrogen chloride. In the water, you would have sodium ions and hydroxide ions. Just like with the acid, you would have hydrogen ions and chloride ions. Okay? So those are the strong acids and strong bases. Writing them this way is consistent with what's called the Arrhenius model, or the Arrhenius theory, which is the idea that an acid is something that produces hydrogen ions, and a base is something that forms hydroxide ions. It's the idea that ions are the key to understanding what acids and bases are. However, there are more modern, developed theories from the 20th century to discuss acids and bases. So let me show you that theory. I'm going to show you one of them right here. And this is called the Bronsted-Lowry theory. Of acids and bases. Okay. The Bronsted-Lowry theory takes into the idea that it's actually the way we define acids and bases is based on reactivity, how they behave. And so an acid, a Bronsted or a Bronsted-Lowry acid, is considered a substance that transfers a hydrogen ion to another substance. And a Bronsted base, a Bronsted-Lowry base, is a substance that accepts a hydrogen ion from another substance. Okay, that's the theory now. Now it's based on reactivity. It's what they're doing as opposed to what they produce. So now, let me show you what I mean by that, just as an example. Let's say that we have HA, and it reacts with B. Let's put it in water, so put them both in water. They collide with each other. Essentially, the HA collides with the B. And in fact, let's write it a little bit more physical. Instead of writing it as a chemical equation, I'll just show you physically what's happening. So I'm going to write the HA this way. Okay, so here's your B, here's your H, and there's your A. Okay, so HA is going to be the acid, and B is going to be the base. Essentially what happens is these two collide. The hydrogen collides with the base, and in the process, hydrogen ion is transferred to the base. So what ends up happening is the A takes a negative charge, and the H takes a positive charge, and now forms a bond with the B. Okay? So what's happened here? An H plus, in fact, let me just put a minus here and a plus here, just so you can see it. So minus plus. So think of it almost like an ionic compound. So the A minus is giving up the H plus to the B. So now the B has the H plus. It's accepted the H plus. So this is what's called the acceptor. It accepted the H plus, and this one is the donor. It donated the H plus. So for that reason, we would call this one the acid and this one the base. Let me show you an example, a real example. So the example is from the textbook. So if we react ammonia with water, okay, ammonia is something you can buy in the store. It's a cleaner, right? It is one of the active ingredients in cleaning glass, tabletops, things like that, ammonia cleaners. Ammonia, turns out, will react with water. I'm going to write the water first. And then the ammonia. And I'm going to use a little arrow to indicate what's happening. Essentially what happens is the water donates an H plus to the NH3, to the ammonia. Now where's that H plus? It comes from one of these two hydrogens. So one of them is transferred. And so then what happens is, again, if you think about water, think of it maybe this way. This could help you to kind of visualize what's happening. Think of water as H plus OH minus. So the H plus is going over to the ammonia. So now what you have is what's called NH4 plus, and then you're left with the OH minus. Okay, so think of NH4 plus as NH3 with an H plus attached to it, right? And this is called the ammonium ion. So what's happened here? The water has donated this H plus to the ammonia, right? So now the ammonia has that extra H plus. It's become the ammonium ion. So it's reacted to form this. So this one would be the base because it's accepting the H plus. And this one would be the acid because it's donating. It's the donor of the H plus. Okay, and then these would be products. Okay, so that's the theory of acid-base chemistry from the perspective of Bronsted Lowry. There are other theories of acids and bases out there. If you take Chem 12, you'll actually learn a third. Okay, so let's do a little bit of terminology here. One of the terminology is what are called monoprotic acids. So these are ones that produce or donate, depending on which theory you're using, right? If you're using the Arrhenius theory, they produce. If they're Bronsted-Lowry theory, they donate. One H plus. They donate one hydrogen ion. So an example of that would be HCl. HCl donates one H plus, or it produces one H plus. There are also what are called diprotic acids. Well, you can imagine what di means, two, right? These produce two H plus ions. An example of that would be H2SO4. Okay, H2SO4 has two hydrogens with which it can donate an H plus. And there are what are called triprotic acids. So these ones produce or donate three hydrogen ions. An example of that would be H3PO4. It's called phosphoric acid. It has three hydrogens. Okay, so in theory, it can produce up to three hydrogen ions in a process. So those are called triprotic acids. The category of di and triprotic acids, we call them polyprotic acids. So we would say that sulfuric acid, H2SO4, is a diprotic or a polyprotic acid, and that phosphoric acid, H3PO4, is a triprotic acid or a polyprotic acid. Okay. There are many of them out there in nature. Now, what I'd like to do is to talk a little bit about what is called neutralization reactions. The terminology we use is to say that acids can neutralize bases. And bases can neutralize acids. And the terminology there is essentially that you're essentially neutralizing the activity of a substance. So an acid produces an acidic solution. A base can reduce the amount of acidity, so it neutralizes some of that acidity, and vice versa. You may be familiar with the pH scale. We actually don't talk about it in this course. It's in the next course. But the pH scale is a measure of acidity. How acidic is a solution? And the scale is based on, typically it's written as 0 to 14. And so 0 to 7 is considered acidic solution. 7 is neutral. And then 7 to 14, above 7, is basic. It can actually go above 14, it can go below 0, but generally those are the scales. So for example, lemon juice. If you measured the pH of lemon juice, you might find it's 2 to 3. Or if you looked at stomach acid is very acidic, or can be. It could be anywhere from 1 to 3. That's considered very acidic, that's very low value. Ammonia cleaner. That might be 11 to 13. So that's a very high pH. Milk, I think is somewhere like 7.1 or something like that. Blood, 7.3, somewhere around there. Okay, so blood's just a tiny, it's pretty close to neutral, but just a little bit on the basic side. So you'll learn more about that in Chem 12, how to do calculations on that. So neutralization is the idea that acids can neutralize bases, they can react with them, and bases can do the same thing. So what we want to do is we want to look at how we analyze neutralization. And so one way to analyze it is qualitatively through molecular, ionic, and net ionic equations. Just like we did with precipitation reactions, right? Turns out acid-base reactions and precipitation reactions have certain things in common. Their form is very similar. Double displacement or double replacement reactions. So I'm going to show you an example that's in your textbook. This is on page 142. So you can follow along with that one. They show, down in the middle of the page, the reaction between hydrochloric acid and sodium hydroxide, NaOH. And they tell you that it forms, the products are water and sodium chloride. Now, solubility guidelines, sodium salts or sodium compounds are soluble in water, so both of those are soluble. Notice the water is a liquid. It becomes part of the solvent. And then acids are generally, many acids are soluble. So if you're doing one of these types of problems, you should make the acid aqueous as well. Okay? So that's the molecular equation. In general, an acid reacts with a base to form water and what's called a salt. A salt, we're going to define a salt as the product of an acid-base reaction. So when acids and bases react, they form salts. And they also form water. Okay? That gives us a working definition of salt other than just saying table salt. Although that one is table salt, NaCl. So now that's the molecular equation. How do we deal with the ionic equation? With the ionic equation, we're going to use the same logic we used with precipitation reactions. If something is aqueous, we break it up into separate ions. If, in the case of precipitation, we said if it's a solid, you don't break it up. In the case of acid-base, if it's a liquid, you don't break it up. Water's a liquid, so we don't break it up. So anything that's aqueous, so that would be this one, and this one, we break them up into their constituent ions. So Na plus and Cl minus, sodium chloride. I'm sorry, not Na plus, my mistake, H plus. H plus Cl minus. Then we have sodium hydroxide, Na plus, OH minus. Product side, water is a liquid, so we don't break that one up. And then sodium chloride is aqueous, so we break that up. Okay, so that's the ionic equation. Anything that's aqueous, you break it up into separate ions. If it's a liquid, you keep it the same. Then we have the net ionic. Okay. How do we deal with the net ionic? Anything that's the same on both sides in the ionic, you just cancel them. So notice there's a chloride on both sides, you can cancel them. There's a sodium on both sides, you can cancel those. So that, if you cancel those, you just have H plus and OH minus, and then you get H2O. Okay? They're neutralizing each other. The H plus is neutralizing the OH minus to form water. Pure water has a pH of 7, it's neutral, so you're neutralizing it. Okay? So molecular, ionic, net ionic. Now, you're going to look at some of the sample problems, but I want to warn you about the problems in your textbook, which is that when you do the ionic and net ionic for the examples they give you, there's something that happens when you're dealing with what are called weak acids or weak bases. They don't ionize completely. So let me show you what I mean by that. If you take MgOH2, which is a base, it's a weak base because it doesn't dissolve completely in water. It doesn't break up into Mg2 plus and 2OH minus. This doesn't happen. So if you're doing this sort of analysis and you're doing MgOH, for the ionic equation, don't break it up into Mg2 plus and 2OH minus. Just leave it intact. And the same goes, so that's a weak base. The same goes for weak acids. You may see examples they give you where they give you a weak acid. So an example of a weak acid would be acetic. HC2H3O2. It does dissolve in water, but it doesn't form very much in the way of ions. It only ionizes about 1%. So when you're doing the ionic equation again, don't break it up into H plus and C2H3O2 minus. Don't do that. Just leave it as acetic acid on the reactant side and acetic acid on the product side when you're doing the ionic equation. And then that will affect the net ionic equation. This will be real apparent when you take a look at the sample problem 4.4, where they show you the reaction of milk of magnesia with hydrochloric acid. Okay? So that's pretty much it for our discussion of acid-base. We don't go into it in much more depth than that. If you go on to take the next course, which is Chemistry 1200, Chem 12 we call it, you'll look at in great detail at acid-base chemistry. So here we're just mainly looking at memorizing some of them, knowing what their definitions are, being able to identify them, and then we go through and we do the molecular ionic and net ionic equations, which you can practice. That's for neutralization reaction.